We introduced the specific heat capacity earlier in Chapter 12. This related the change in temperature of a substance to the amount of heat flow with equation 12.4. In this expression, m is the mass in kilograms, and c denotes the specific heat capacity with units of joules per kilogram per Celsius degree. However, it is useful to express the amount of material as the number of moles, n, as opposed to kilograms. Therefore, we replace Q equals mc delta T with the following analogous expression, where the capital letter C refers to the molar specific heat capacity with the units of joules per mole per Kelvin, and the change in temperature, delta T equals T final minus T initial, is in Kelvin. For gases, it is necessary to distinguish between the molar specific heat capacities Cp and Cv, which apply under conditions of constant pressure and volume respectively. Using the first law of thermodynamics with an ideal gas, we can show why the values of Cp and Cv are different. To determine the molar specific heat capacities, we must first calculate the heat Q needed to raise the temperature of an ideal gas from T initial to T final. The first law tells us that Q is equal to delta U plus W, and the change in internal energy of an ideal monatomic gas is U equals 3/2 nRT. As a result, delta U is equal to U final minus U initial, which equals 3/2 nR times T final minus T initial. Earlier in this chapter, we showed that during an isobaric process, or one that occurs at constant pressure, the work is given by W equals P times V final minus V initial. For an ideal gas, PV equals nRT, so that the work becomes W equals nR times T final minus T initial. On the other hand, if the volume is constant during the heating process, or an isochoric process, delta V equals 0, and the work done is 0. The calculation of the heat for these two processes is summarized here. The molar specific heat capacities can now be determined by using Q is equal to Cn delta T, where for Cp we use the result for the heat at constant pressure, and for Cv we use the result for the heat at constant volume. Gamma is defined as the ratio of the molar specific heats, and for an ideal monatomic gas it equals 5/3. However, many gases are not monatomic, but instead consist of molecules formed by more than one atom. Oxygen in our atmosphere, for example, is a diatomic gas, since it consists of molecules formed by 2 oxygen atoms. Nitrogen, which is the most abundant gas in our atmosphere, is also a diatomic gas. Diatomic molecules can possess multiple forms of internal energy. A single atom monatomic gas exhibits only translational motion, whereas an ideal diatomic gas can exhibit translational, rotational, and even vibrational motion at sufficiently high temperature. The result of these additional motions is that the equations for the molar specific heats do not apply. Instead, if the temperature is moderate, so the atoms in a diatomic gas don't vibrate, then the molar specific heats are given by Cp equals 7/2 R and Cv equals 5/2 R, such that gamma is equal to 7/5. The difference between Cp and Cv arises because work is done when the gas expands as heat is added at constant pressure, whereas no work is done when heat is added at constant volume. For a monatomic ideal gas, Cp exceeds Cv by an amount equal to R, which is the ideal gas constant. In fact, it can be shown that this result applies to any ideal gas.